All right. Looks like we're in business. So, before we get to 9:35, any questions on the project or any questions in general for me? No? Everything working well? Good. Okay, so maybe let's start from remembering what we got last time. So just a brief review of what we had last time. We started talking about iterative methods for solving large linear systems. And we introduced the first type of iterative method, that's the Jacobi method. So the Jacobi method splits a matrix into diagonal parts and off-diagonal parts. And move the diagonal part on the left-hand side and move the off-diagonal parts to the right-hand side. We also programmed the Jacobi iteration last week and took a look at the result of the Jacobi iterations, right? And who remembers what's the behavior of the solution error? So after many iterations, what does the solution error look like? Low frequency, very smooth, right? Okay, good. So today, let's actually start from that. So we are going to be talking about multigrid. So iterative method and multigrid. And the starting point is exactly the end of last lecture. So we are going to start with the Jacobi iteration. We are going to take advantage of the fact that after many iterations, the error, the solution error, which is defined as the difference between the exact solution of the linear system and the iterative solution at iteration k. So the solution error after k, after many iterations when k is large, is very smooth. So the idea of the multigrid is to save computation time and accelerate convergence by solving the error equation, which tries to correct that error on a coarser grid. That's what multigrid means. So to recap, after a few iterations, the solution error is smooth, and then we derive another equation that gives us that solve for that smooth solution error, and we solve that equation on a coarse grid, and then correct the fine grid solution with the solution on the coarse grid. So that's the overall idea of this lecture. And so here I'm starting to get into details. First of all, let's review what Jacobi iteration does. Okay, so this time instead of using the Lerner picture, so this is the picture we open the folder. So remember, this is the picture we looked at last time. It's a pretty tiny one, actually. I have to really zoom in for this to be large enough, but it's actually a 19 kilobyte picture that small. That makes the linear system still tractable. It's not too large. This time, we're going to be looking at a much bigger picture like this. We are going to use an airplane as an example. So this is a 1023 by 1023 image. So when you are solving a linear system with this being the solution, what is the size of the linear system? What is the size of the matrix? Yes? It's about 1,000,000 by 1,000,000, right? Today we are going to use multigrid to solve a 1,000,000 by 1,000,000 matrix. We are still going to use the example of Poisson's equation. Okay, so let's first import that into MATLAB. So import data. Okay, finish. So I get an array called airplane. That's a 1023 by 1023 by 3 matrix. All right. So let's say U exact. That's our exact solution is equal to 0, 1025. that's the dimension of the matrix plus 2 because I also need boundary conditions. Okay, that's my U exact. All right, let me actually let me code up my B. All right, so I'm going to say n is equal to 1024. That's the size of the grid, and dx is equal to 1 over n. I'm going to say B is equal to 0 n plus 1, which is the same size as U exact. And U exact from 2 to n minus 1, 2 to n minus 1, that's like the interior of U exact, is equal to airplane. So the thing I just imported divided by 156. All right, let me make sure I get U exact to be correct. Okay. That doesn't seem to be right. I think I need a float. Otherwise it's a integer divided by integer. It's either 0 or 1, so I get a black or white picture. So I need to convert it to float then. Okay, double. All right, that works. Now I get a grayscale picture. Otherwise, I get a black or white. It's 0 or 1. All right. Now that it works, I have my U exact. Then I'm ready to compute B. So I already defined B as a zeros picture, a zeros array. So I'm going to for I equal to 2 to n minus 1, for j equal to 2 to n minus 1, and B of ij should be equal to U of ij minus 1, Ui of ij plus 1, plus U of I plus 1j, Ui minus 1j, minus 4 times Uij. That's a discretization of the second order derivative in x and the plus second order derivative in y divided by delta x squared. Do we all recognize that finite difference formula by now?
Okay, sorry for that. All right. Oh, undefined function variable u. So let me say u is equal to u exact. Okay, and repeat what I had before. Okay, so now we have a right hand side b. Just so I am sure what b is. I mean, it's a very rough picture. So basically, it's the second derivative, the Laplacian of the picture u. All right, it shows kind of the contours of the image pretty well. Okay, so here in this lecture, what I'm going to do is I'm going to solve the equation ax equal to b, assuming we don't know the u exact. Of course, we do have a u exact, so we are going to use the u exact to assess the solution error. And by the way, this is a very common way of assessing how good a numerical procedure is. To first construct an analytical solution or some known solution, and then compute the right hand side, okay, of either a discretized system or an analytical PDE, and then give that right hand side to a solver and ask the solver to reproduce the exact solution that I know beforehand. And that gives me a good handle of what the error is. That can be applied both to solving linear systems and the numerical schemes of solving PDEs. All right. Okay, so now I have the B. So let's first review our Jacobi iterations. Okay, so in this time, instead of coding directly on this, I'm going to make a function called Jacobi.m. The inputs of the Jacobi is the solution is the initial guess and right hand side, and my output is my next solution at the next iteration. All right, and what I'm going to do is I'm going to say, okay, So first of all, I'm going to get the dimension of u. So n is equal to the size of the first dimension of u minus 1. Here, the both dimensions of u is 1025. So n is equal to 1024. Okay, I'm going to recompute dx is equal to 1 divided by n. I put 1 point just to make sure it's a floating point. When I do the division, it's doing floating point division. Okay, and then I'm going to make a u next equal to zeros n plus 1. Here I'm going to implement Jacobi iteration. For I goes from 2 to n minus 1. For j goes from 2 to n minus 1. I perform u next of ij is equal to the inverse of the diagonal matrix times b minus l plus u times my previous u. So the inverse of the diagonal matrix is equal to minus dx squared divided by 4, right? Okay, then times bij minus, I'm going to put a dot 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 so that I can continue next line. It's uij minus 1 plus uij plus 1 plus ui plus 1j plus ui minus 1j. And I need to divide by delta x squared. Is that right? Any bug in this? So here are the off-diagonal contributions to the matrix. Right? These are all the off-diagonal terms. The only thing that I didn't include is the minus 4 times uij, which is the diagonal. Any questions? Please raise any questions when you look at the code. I know sometimes I'm coding too fast. All right, so just stop me when you have any questions. Cool. Okay, and I put to end over here. That's my Jacobi iteration. So u next is exactly the return variable. All right. This function performs one iteration of the Jacobi iteration. All right. So if I have an initial guess of zeros, I say u is equal to Jacobi of u and b. I performed one iteration. Okay, here's one iteration. Here's another iteration. Here's another iteration. That's the good thing about a function, right? Okay, so let's say I am sure of u. You don't see anything, so let me boost it up times 10. Again, we see like a contour of this, right? And if we look at the solution error would be u minus u exact or u exact minus u. Let's look at u exact minus u. You don't really see much of a difference. Let me make another figure so that we can compare. Okay, 1, 2. I can see a little bit on my screen, but like the solution error after a while is like a smooth version of the solution here. Right? To make it more obvious, let me do 100 iterations. Okay, now you can see more clearly. What is this orange over here? Okay, I must be doing something wrong on the board.